So we have a very different seminar today compared to other seminars because we have two speakers. And we will get started with Ben Johnson. And most of you probably know Ben. He has been ASP postdoc here at NCAR. That was about, you said, 10 years ago, right?
Yeah, that's about, yeah. And
Ben is now at the UK Met Office. He's a senior scientist there. Back in Boulder, he worked on the parametrization of large-scale cloud properties in the CESM model, and moved then to the UK, where his research is now mostly focused on analyzing aerosol measurements, improving aerosol models in climate research, and he's also doing numerical weather prediction. A main focus of his work is on dust and biomass burning aerosols, and I think the biomass burning aerosols, that's what he's going to talk to us today, right?
Yes, that's it. Thank you, Gabby. Yeah, it's great to be back. As Gabby said, I was here 10 years ago as an ASP, and this is my first trip back to Boulder. Graham and I went to the Aerocom meeting in Steamboat last week, so I couldn't resist the opportunity to come back and see some of you guys and share what I'm doing now. So I'm going to talk to you today about the simulation of biomass burning aerosol. And this is some work that I've been doing following a project in Brazil that I'll tell you about, where we were looking at smoke over Amazonia. So before I get started, I'd just like to acknowledge my co-workers from the Met Office. So you have a whole range of people there, but also Graham, who's speaking after me, developed the aerosol model that I'm going to be talking about. We work also with the University of Manchester and University of Leeds in the UK. Can you all see the screen? Because it seems quite light. Is that okay?
There's a switch behind you.
A switch behind me. Okay. Yeah, that's better. I can see the slide as well now. Okay. So I'm working with Jim Hayward is my supervisor. So he's now also at the University of Exeter in the UK. So without further ado, let me move on. So today I'm going to talk to you about the Met Office Hadley Centre's Earth System model. I'll just give you a heads up on what we're doing with that, and talk to you about the aerosol models that we've been developing for this. I'll also tell you about the Samba field campaign, which was a measurement campaign over Brazil that we did about 2 years ago. And I've been using this the field data to look at the aerosol models and evaluate how well we represent biomass burning aerosol. So hands up if you've heard of HadGem2 to start with. Okay, so HadGem2. So the UK Met Office Hadley Centre has been developing climate and Earth system models for a number of years now, but just recently we've enlarged our activity to take in a lot of university contributions in the UK. And so we now have a UK-wide project to develop the next Earth system model. We're calling this UK ESM, UK's Earth System Model. And it's a collaboration between the Met Office and universities funded by the Natural Environment Research Council. And so our plan is to develop this model as a follow-on from HadGem2 for CMIP6 and beyond. So it's going to be built on HadGem3, which was a kind of a stage, and the next stage in our development cycle. And you can see it's got various components that are coupled together. The atmosphere now has a new chemistry and an aerosol module called UKCA. The ocean model we use is NEMO, and we have Medusa biogeochemistry as part of that. The land model is called Jules, and we have Triffid vegetation, which is interactive vegetation. And we represent the hydrology and the soil and the full carbon cycle in this model. In terms of ice, we have an ice model called SICE for the sea ice, and then bicycles for the ice sheets. Now, I'm afraid don't ask me anything more about all of the other components. That's kind of beyond me, but I'll tell you a little bit more about the aerosol now. Okay, so this is the GLOMAP-mode aerosol scheme, sometimes referred to as UKCA mode, where UKCA refers to the name of the project. This was developed by Leeds University, and it's the aerosol scheme that we're developing for the UK Earth System model. We've now implemented it in our global model system, and we've just been tweaking it over the last year or so to get it performing well. But in essence, it's a modal scheme where you have the aerosol size distribution represented by a number of different size modes, as you can see in this diagram. And within each size mode, you have an internal mixture of various aerosol components. And so at present, we have sulfate, black and organic carbon, and sea salt in there, and we're developing the nitrate and dust code, and that will be added in the near future for the Earth system model. So it will have all of those components when we're done. And the idea behind this scheme is that it simulates the full life cycle of the aerosols, and you can see the range of processes. I won't go into it. And this is a replacement for what we had before. Beforehand, we had a scheme called Classic, which just represented each aerosol species as a single tracer. And we would just add vector the mass of a single tracer, and the properties of those species were prescribed. So what we have now is much more sophisticated. We can represent the internal mixing now, and we represent the physical processes and chemical processes at a much greater level of detail. So I'll just show you now, just quickly, how our aerosol schemes are performing in HAGEM3. So as I said, HAGEM3 is kind of a stage before the Earth system model, UK ESM. So it's what we're currently testing with. And so this is now aerosol optical depth globally, and an annual mean at 550 nanometer aerosol optical depth. And so on the far left, you have HAGEM3 run with the classic aerosol scheme. And then you have the modal scheme, UKCA mode, and then I'm comparing against MODIS, MODIS Collection 5, 2002 to 2006. And so you can see there are differences in the global distribution of aerosol between these two models. Particularly, for example, you can see over Eastern Europe in UKCA mode scheme, we have a lot more aerosol there now. Maybe that's overdoing it. But we have some improvements. For example, if you look at the northern high latitudes over the continents, we now have more aerosol up there, which agrees better with MODIS. We're still not getting quite enough tropical aerosol. So if you look, for example, in Brazil or Central Africa, we're slightly underdoing the biomass burning aerosol and the dust in those regions. So there's still things that we're trying to get better. And I think I'll move on now to talk about the field campaign from Brazil. So this is Samba. So I was one of the PIs on Samba, and it's the acronym refers to the South American Biomass Burning Analysis. This is something we did 2 years ago. It was a collaboration between the UK and Brazil. So we had the Met Office, the Natural Environment Research Council, and our partners were the University of Sao Paulo and INPE, which is the Brazilian National Space Institute. And they do a lot of research into biomass burning, air quality, satellite retrievals, etc. So the project involved taking the UK FAM aircraft. This is the UK's large research aircraft, and it's a fairly comprehensive tool. We have chemical, aerosol, radiation, meteorology, dropsons. We have a LiDAR. So it's a sort of an all-singing, all-dancing aeroplane, and we fit it out slightly differently for different projects. But in this case, it was an aerosol and kind of chemical focus that we had for this campaign. So we based the aircraft in Portobello, which is the southernmost of those red squares on the map, and we went all over in this green highlighted region. The next square up in the north, that's Manaus, where there's a lot of ground kit was located. There was also ground sites located in Portobello in the southern site. And those ground sites are run by the University of Sao Paulo. And they have a long-term record of monitoring aerosol chemistry, and they have LiDARs and all sorts of things. So there was very much a coordinated effort between the ground and the aircraft. So now I'm using the aircraft data to evaluate the model, but just before that, this is a blow up now of South America, showing again the aerosol optical depth in our models, and this is kind of showing you how how it's comparing against MODIS. So we have a panel of 4 plots. The observations from MODIS are in the bottom right hand, and then we have various models with different tuning levels. So we have on the top left we have classic, and to try and get the aerosol levels up, the biomass burning emissions have been scaled up by a factor of 2. Now when you go across to UKCA mode, so top right hand panel, this is the model run with the scaling factor of 2, but you can see there's less aerosol. If you go down to the bottom left-hand corner, then you have a UKCA mode, but we're scaled up by a factor of 4. So you can see, actually, to get the models to agree with the observations, it's necessary to scale up biomass burning emissions, which is unfortunate because one doesn't want to do scaling. But this is something we found in our model, and it's something that has been found in many other models as well. For example, ECMWF, they scale up their emissions by a factor of 3.4. So it's not an uncommon thing to do, but it highlights the fact that there's a lot of uncertainty in biomass burning emissions and biomass burning processes, and it's it points to the need for more research in how to get emissions to give you the right aerosol loading in models. The other thing is that you notice, of course, is that the amount of scaling that you need depends on the aerosol module that you're using. So in the case of classic scheme, for example, the mass loading was higher because there's different representation of aging in the model. So when you have a biomass burning aerosols, sorry, is there a question?
So why do you think then the problem is in the emissions? If the difference between processes in the model can give you a factor of 2, and the other factor of 2 could just as well be processing rather than emissions.
Yeah, that's very true. Yeah, that's a good comment. So I guess the reason why I think the emissions are underdone is because this has been tried in a number of different models, and most models have found an underestimation. But it's true.
All underestimate secondary organic aerosols.
Yes. So the models could all be wrong. So there is an Aerocom activity based around this problem that I might tell you a little bit about. I have some results that go into that.
How much variability is there from year to year?
There's a lot of interannual variability of biomass burning aerosols, so you have to take an average over 5 or 10 years before you can really see. Yeah. Okay, so this is now looking at the composition, which hopefully is less variable from year to year. And so I have the 2 aerosol schemes, that panel of 8 plots. And so you have UKCA mode aerosols on the left hand, and then the classic, the original scheme on the right. And I'm looking down, so on the top you have the black carbon. This is just showing the column integrated burden of the aerosol, the different types of aerosol mass. So you have black carbon, then you have organic carbon, and then coming down you have the sulfate, and then on the bottom I'm showing just the fraction of black carbon from the total aerosol. So you can see, although the regional distributions are similar, there's some differences in concentration and the distribution. But the most critical thing in terms of the optical properties of the aerosol is actually the black carbon, because that's the absorption, where the absorption comes from. And you can see actually in the bottom plots there's a huge difference in the black carbon content in the 2 schemes. And this becomes important for the optical properties. So we're trying to validate this against the ground observations. So this plot here is looking at the observations from Portobello, from the ground site, and I now am showing it in terms of the mass fractions. So you can see in the observations and the models, organic carbon dominates this aerosol, but there's a lot of discrepancy between the observations and the 2 models in what makes up the remainder. So the model's showing more sulfate, which is mainly ammonium sulfate, but showing slightly less black carbon than the observations. But the modal scheme has got something closer to the observations for the black carbon, so at least I'm pleased about that. So this is now showing the size distribution of the aerosol. And so what I've got here is a range of instruments from the aircraft, and I've essentially averaged over all of the flights that we did in the region around Portobello, looking at the biomass burning aerosol. So only selecting out the runs that we did through biomass burning aerosol layers, and I'm just taking a straight kind of average of all of those to come out with something that I can compare against the model in a sort of more looking at the model's climatology, the mean kind of representation of the aerosol. So you have various instruments like the PCSP, the GRIM, the SMPSs. They all do different parts of the size range. And then we have the two models. So in the red is the UKCA mode model, and then in the blue is the classic biomass burning aerosol. And so you can see the red line from the modal scheme. It picks out most of the size range quite well, but the classic aerosol scheme was never really intended to represent the full range of particle sizes. It only has a mode in the accumulation mode, in the kind of the optically active region of the aerosol size spectrum. So whereas it might give you something to base your optical properties on, if you're interested in the full spectrum for example, the processes in the aerosol and the microphysical interaction with clouds, you really need something that spans the spectrum a bit more. So it's nice to see that the modal model is doing quite a good job in this comparison. And I now have a comparison against Aeronet. So these are the Aeronet network of sun photometers, and these do retrievals of the aerosol properties, including the size distribution, basically by looking at the radiance in the sky through a large scan. And from the scattering that they see at different angles, it retrieves the aerosol size distribution and the refractive index of the aerosol. So this is now looking at a particular site in Brazil, Alta Floresta, and I've put together a 14-year mean from all of the Septembers. And so the black line in the plot is the Aeronet retrieval. And then we have two instruments from the aircraft. So we have the PCSP in the green, and then the GRIM. Now, but both of these are optical particle counters. It's nice to see that there's some agreement with the PCSP, at least for the fine mode of the aerosol. But what's even more encouraging for me as more of a modeler now is to see that the modal scheme on the bottom plot, if you look at the red line, UKCA mode is now giving a very, very nice agreement with the aerosol retrieval in the fine mode. There's a little bit of discrepancy in the coarse mode, but Aeronet retrievals in the coarse mode are perhaps a little bit uncertain anyway, so I'll skim over that. But you can ask me about that at the end if you know about that. Okay, so I'm now looking at the aerosol absorption. So the single scattering albedo is one way of representing absorption. So it's really the scattering over the extinction. So if you have a value less than 1, then it's more absorbing. And you can see the two aerosol schemes now. The classic is giving quite weakly absorbing aerosols. When we look at biomass burning aerosol in the observations, we typically get values of about 0.8 to 0.9 for this kind of aerosol type. So that seems to be way too scattering. When we look at the UKCA mode model, because it has more black carbon in the aerosol, we're getting values that agree a little bit better with the observations. So we're getting average values of around 0.9, 0.92 in the centre of the biomass burning region. And this agreed quite well with the Aeronet retrievals and also with the in situ data from the aircraft. So I'm pleased that the new scheme is doing better. I think I'll perhaps skip over this one in the interests of time. And so this is the Aerocom experiment I referred to earlier, which is about trying to understand this problem of needing to scale up the biomass burning emissions. And so the outline of the experiment, there's two different aspects to it. One is just straight looking at the sensitivity to scaling the emissions by various factors. But there's also another part of the experiment which is looking at Why is it necessary to scale up the emissions, and is that dependent on model processes? Is it dependent also on where the emissions are injected? Because for biomass burning aerosols, you have large smoke plumes that will tend to distribute those emissions across a range of heights, and quite often large fires will inject the smoke into quite high altitudes, maybe up to 5 kilometers or so. So if you just release the emissions at the surface level, you don't get the right kind of vertical distribution of aerosols. So there's various processes that are being looked at in this Aerocom experiment. I'll just show you, perhaps, in the interest of time, I'll perhaps just show you this one where we're looking at the impact on the vertical distribution. So the black line in this plot is the observations from the FAM aircraft, and what I've done here is I've taken all of the profiles that we made in and out of Portobello, where we were based, averaged them all up together, and then I'm comparing against the model, taking the grid box over that location, and the monthly average during the period that we were taking the measurements. And I've got 3 different simulations that I'm showing. So to start with, the standard kind of model is the one in blue, where in our model we release between the surface and 3 kilometers to try and represent the fact that the aerosol emissions are lofted over the source regions. The red line is where we just release the aerosol at the surface, and we would then expect the boundary layer mixing to mix that up. But as you can see, the boundary layer mixing doesn't really mix it up enough to represent what we see in the observations. And actually the one where it's lofted does a lot better. The next model line you see is a sensitivity study where I've actually turned off the convective plume scavenging. So this was, for example, in the convection scheme, you have a vertical mass flux of traces in the model. And if you switch on this new plume scavenging scheme, then it will remove the aerosol from that vertical flux based on the precipitation that's formed in your convective tower. So the idea behind the plume scavenging is that it tries to remove the aerosol efficiently, representing what happens in deep convection. And if you don't have that scheme on, you see actually too much is distributed vertically. So it shows you that there's a lot of sensitivity to how you represent kind of aerosol removal processes. That's the other side to the problem. You might well fix the emissions, but if you're not removing the aerosol correctly, then the loading in the atmosphere is going to be wrong again. So I think I'll conclude at this point, and I hope I've shown you something interesting today about our model, and that we've got this aerosol scheme UKCA mode that's producing a fairly good simulation of biomass burning aerosols. It has some improvements. For example, the size distribution is more realistic. The level of absorption of solar radiation is more realistic. But there's also this problem that we're looking into about why we have to tune the emissions. And so I think I'll wrap up there and take some questions. Thank you.
Thanks, Ben.
So just for my clarification, what's the relationship between this model and the unified model? And the other question is, so what about now you're in an ESM, what's the climate impacts of this, and what's the uncertainty in these choices on the climate impacts?
Right, okay, yeah. So first question, so at the Met Office we have a unified modelling system, which is one GCM for all range of from numerical weather forecasting all the way up to climate and Earth system modelling, and it's a common code base, and all of the physics is the same throughout all applications, with various switches and decisions that you make. But basically, the idea is that your climate should be the statistics of the weather. So that's the kind of strategy. So when I talk about the Earth system model, it's kind of taking the unified model but adding new things in. Say, for example, the ice sheet model, the biogeochemistry. These are things that are added on top of that to make it an Earth system model. Does that make sense? In terms of climate impacts, I guess that's future work for me. At the moment, we're evaluating this scheme really on how well it represents the aerosols, and to look at the radiative forcing and to look at the climate impacts is next for me. But most of our work on kind of climate impacts, radiative forcing, was done for CMIP 5. That was based on HAGEM 2, so it's kind of in the pipeline that we'll be writing more papers on UK ESM in the next few years.
A few slides back where you had just before you switched gears, you were looking at the measured versus the model. In the,
Which one?
There was two graphs on the paper or on the slide.
Okay, further back than this?
Yeah.
Okay. Was
Close.
it to do with absorption or?
Even more, just the one right before this one, I think. Yeah, this one.
Right.
Where you're looking at the difference between the model and the observations. I was wondering if you noticed any dependency on altitude with the difference between the model and versus the measured.
Right. Okay.
Because there's the hump there in the middle,
Yeah.
between 1 and 10.
Right.
And I was wondering if that has anything to do with the altitude that the observations were taken at.
Yeah. So these observations, because they're remote sensing retrievals made from the ground, so they're averaging up over the whole column of the atmosphere. So to try and compare the model with that, I've essentially taken an average through the column of the atmosphere. So we're comparing both like by like. When I've looked at the observations from the aircraft, however, you do see changes in the distribution. So you tend to see more the coarse particles lower down, and as you go up higher, you tend to also see slightly finer kind of aerosols more predominantly. I haven't really looked at whether the model does that well or not, but that could be quite interesting to look at.
You showed that about 80 or 90% of the aerosol mass is organics.
Yes, that's right. Yeah.
And so I guess I have two questions. One is what fraction of those organics are primary versus secondary?
Yeah.
And that, of course, bears on the emissions questions.
Yes.
And the other question is, what optical properties at 550 are you assuming? What single scattering albedo are you assuming for the organics, or is it purely scattering, or is it somewhat absorbing?
Yeah. So it's a good question. So in the classic scheme, we have a kind of an assumed growth of the organic carbon. So most of the mass is emitted as primary, but then there's an assumed growth which adds about another 60% of mass. And it had just an e-folding timescale of 6 hours for that growth. So that's very crude, but it was based on observations from Safari that showed that kind of development of downwind in a large smoke plume. Now with the UKCA scheme, we try and represent that process explicitly, so we have a condensation of VOCs onto the aerosols. So that does add some mass, but it doesn't add as much as 60%, it's more like 20-30%. And we represent the VOCs through things like monoterpene oxidizing and condensing onto the aerosol. But there's a lot of debate, even in the observations in the literature, as to how much mass is added to the aerosol, how much of it is primary. And actually, when we looked at the observations from Brazil, we saw that there really wasn't much mass added compared to what's emitted. For example, if you look at the ratio of carbon monoxide, the excess of carbon monoxide, over the excess of the organic carbon mass in large plumes going downwind, you'd see that ratio was pretty much flat, which suggests that there's not really very much secondary being added, or that there's an equal balance between addition and evaporation of the organics. Whereas observations in South Africa from ground sites have shown completely the opposite, a factor of 10 added to the mass. So it's kind of not clear how to interpret this disagreement in the literature. Does that answer your question? Okay. The optical properties. Yeah, at the moment we assume the organic carbon to be non-absorbing, but I want to tweak that as a follow-on bit before I look at the radiation, because there is a lot of brown carbon in the biomass burning emissions, and there's now a new data set that just came out recently that we can use. So I think that will increase the absorption and probably make the radiative transfer a lot better.
Thank you. Any more questions? Then thank you very much, Ben.
Okay.
I think that was a very nice demonstration of how careful we have to be that we blame everything on the emissions, which we tend to do.
Yeah.
Okay, so let's move on to Graham and our second talk of this seminar. Graham Mann, he's been at University of Leeds for 15 years, where he's also done his PhD. He is there a permanent research fellow funded by the National Centre for Atmospheric Science on the UK Chemistry and Aerosol project. So we stay in the topic of aerosols. And his main research is on the impacts of aerosols on climate and air quality. And he's really looking at all different types of aerosols, ranging from biogenic to dust aerosols to stratospheric aerosols. And he's very active in model development, which we will talk a lot about today. He is also the PI on the EU-funded MAC2 project. And he is leading also the global aerosol microphysics working group within the international Aerocom model intercomparison. And if we see the slides today.
I'm just trying to recover the cursor here, because so I may need some help here to quit this presentation.
Did you just hit escape maybe?
Escape? No, so I tried that one.
I need your help, please.
Yeah.
Sorry, some technical difficulties.
It's the way it's it's not duplicating the screen when we go to presentation mode. Maybe.
Did we escape out of this again?
Control on.
Oh,
there we go. It's back. Yeah, that should be okay now. Yeah, so I think if we go to to close it.
Yeah, so we go from current slide.
Yeah, so yeah, it's the other presentation I need. So that's.
And now we have the wrong presentation.
That's okay. You've got the right one now.
So the presentation today will be actually about quantifying the radiative forcing from the 91 Mt Pinatubo eruption. So we stay with aerosols, just move to a different type. Thank you, Graham.
Thank you, Gabby. Yes, so this is I'm from the University of Leeds, and this work is related to the UKCA initiative that Ben already described. So it's a collaboration between Leeds and the Met Office and the other partners in UKCA, the University of Cambridge, and also Nicholas Bellowin at the University of Reading. So I'm talking today about stratospheric aerosol, and in particular the large perturbation to the stratospheric aerosol that occurred after the Mt Pinatubo eruption in 1991. So I'll first of all discuss the life cycle, really, and consider the life cycle of the stratospheric aerosol and the processes that are shaping the evolution of the aerosol in the stratosphere. So we have the major circulation being the Brewer-Dobson circulation, with large-scale upwelling in the tropics, and the life cycle really begins from nucleation in the upper troposphere, and these particles are then transported into the stratosphere, where they're shaped by microphysical processes. So they have much longer lifetimes in the stratosphere compared to the troposphere. So the processes, condensation and coagulation, can act on the particles and grow them. And even though particles are relatively small, because of their long lifetimes, sedimentation can play a key role in their removal from the stratosphere, and then dynamical processes in the stratosphere shape the lifetimes of these particles. So from the tropical reservoir in the stratosphere, and their transport meridionally towards the higher latitudes, these dynamical and microphysical processes in combination really control the evolution of the aerosol in both background conditions, and then with a major volcanic perturbation to the system, big injection of SO2 into the stratosphere. Then really to understand how the aerosol evolves, you need to consider these microphysical and dynamical processes in the model. So the UKCA model that Ben introduced includes the aerosol microphysical scheme, which includes these processes, and the model configuration I talk about here is the high top version of the Hadley Centre general circulation model. So it has a well resolved stratosphere, and the dynamical processes are well resolved. We have a stratospheric chemistry scheme in the model to represent also the evolution of the ozone in coupling with the dynamics and the aerosol. So yeah, if we consider the impacts of volcanic eruptions, then a large quantity of SO2 can be injected into the stratosphere, which then forms sulphuric acid in the gas phase, which then rapidly is taken up into the aerosol. So this mainly grows existing particles to much larger sizes, that can form also more new particles from new particle formation. So this is really then creating a much enhanced aerosol, stratospheric aerosol layer, which exerts a direct surface cooling, and then of course the enhanced aerosol also perturbs the chemistry in the stratosphere. So a much enhanced surface area enhances heterogeneous chemistry, which can cause a chemical ozone loss, as well as perturbing the chemistry in other ways. And then we also have the enhanced aerosol has grown to much larger sizes, where you actually get a heating of the aerosol layer as a result of the absorption of solar near infrared and also terrestrial long wave radiation. And this introduces this heating of the tropical stratosphere for a tropical eruption like Pinatubo, introduces big change, a dynamical response in the stratosphere. So the meridional temperature gradient is changed considerably from this heating in the tropics, and there's several dynamical responses in the stratosphere that are introduced as a result of that. So the heat transport is changed from as a result of the change in circulation. We have increased tropical upwelling from the heating, which introduces lower ozone air, which introduces a dynamical ozone loss in addition to the chemical ozone loss. And we also have then change in the aerosol dispersion itself, and changes in water vapor. So I guess these things are well known, but our model is really trying to represent all of these, many of these processes in a coupled framework. So we have the stratosphere troposphere chemistry. We have a well-resolved stratosphere for the dynamics, and we have an aerosol microphysics scheme to represent the evolution of the aerosol in response this large perturbation. So this is the model, as mentioned already. So I don't need to say too much, but it's really been a collaboration over coming up to 10 years now between the Met Office and universities in the UK, as Ben mentioned. So we have fully coupled tropospheric and stratospheric chemistry schemes, the GLOMAP aerosol microphysics scheme that Ben mentioned. We have the indirect effects from the aerosol cloud interactions in the troposphere, represented fully mechanistically with consistency with the aerosol properties. And in these simulations, really, we're focusing on composition dynamics, interactions, and the radiative coupling between the aerosol and the ozone and the dynamics. So the Mt Pinatubo eruption, so measurements show that between 14 and 23 teragrams of SO2 is injected, was present in the stratosphere shortly after the eruption. And the stratospheric aerosol loading peaked several months later. But if you work out actually the burden of the global burden of sulphur in the SO2 and the peak value from satellite measurements in the aerosol, then actually there's about almost only half of that sulphur was present in the aerosol at peak loading. So 7 to 11.5 teragrams of sulphur in the SO2 resulted in a peak aerosol burden of only about 3.7 to 6.7 teragrams. So this is something that the models that have represented the aerosol interactively struggle to reconcile, really. And in our simulations, we've done two control simulations of 10 and 20 teragrams of SO2, or 5 and 10 teragrams of sulphur, to represent the range of aerosol burden that's shown in the literature. So this is just accepted in ACP. The results I'll show, a paper led by Sandeep Dance. So we can consider, actually, in relation to that, I'll show this now, the evolution of the global burden of SO2 and aerosol, and the sulphur burden evolution. So if you see the red line, there is the global burden of SO2 in sulphur. So it's 10 teragrams just after the eruption in the 20 teragram injection. That rapidly is converted into aerosol. So you see the red line dropping down very rapidly, and then the blue line shows the aerosol global burden, which peaks just over 10, because we have the tropospheric aerosol as well. So the green is really picking out the stratospheric aerosol evolution. So we see in those simulations about 90% results in the aerosol, whereas the observations in black here, derived from the HERS satellite measurements, suggest, so saying only around 5 teragrams of sulphur. So our 10 teragram injection is shown in the dashed line, and that actually much better captures the variation in the global burden. So that's one of the findings from our simulation. So we see this here when we compare the aerosol optical depth against satellite measurements. So the top left and the top right are our 20 and 10 teragram simulations. We're showing the zonal mean aerosol optical depth against time through the period. So we see in the first few months after the eruption, the plume is confined into the tropics and is only dispersed to the southern hemisphere, to mid latitudes after a few months, and we see this initial transport to the southern hemisphere in September, October, and then to the northern hemisphere much later in the northern hemisphere winter, in January, February, and then peaking in around March. So we see this in the satellite measurements. This is really representing the evolution of the plume, really in good agreement with the observations from SAGE. So from the SAGE satellite in the bottom left, we are much too high in the 20 teragram simulation in the tropics, and it's known that the SAGE instrument saturates in that tropical region, so that overestimation in the tropics is somewhat expected, but really in the mid latitudes there we're capturing that in the 10 teragram run, the aerosol optical depth evolution really well, and including this higher AOD in the southern hemisphere, the transport to the southern hemisphere in the second year after the eruption, higher than the first year. So this is very encouraging from the perspective of the model capturing the dynamical processes. I should say that these runs are actually not, in these simulations we haven't coupled the aerosol to the dynamics. We're actually running in double call mode here, where so we actually don't have those dynamical feedbacks in these simulations. So I'll go on to talk about that afterwards. But here we're just running with the model uncoupled from the dynamics in the aerosol radiative effects. But the ozone is radiatively coupled. So here we can compare in the tropics against the extinction from the SAGE measurements. We're capturing really the peak, extinction, and decay time scales quite well. Although there's this overestimation in the initial period, you can see against those measurements. And if we look in the mid latitudes, where there isn't this issue with the SAGE signal saturating, we're really capturing in the 20 teragram run. Although that was giving too high AOD, it's actually giving very good representation at each of these levels and at both of those wavelengths in the northern hemisphere mid latitudes. But really, one thing we focused on, in addition to the optical properties, to understand how the size distribution is evolving in these simulations. So if we look at the plots on the left hand column there, the top left is actually a vertical profile evolution of the surface area density 15 to 20 north. So we can see the evolution of the main plume there in the vertical profile. But if you consider also in the same profile the effective radius, which is giving the variation in the size distribution, you can see a gradient in the vertical with much larger effective radius at lower in the lower stratosphere and smaller sizes higher up as a result of the sedimentation. And if we look at that spatially on the right hand plot comparing to measurements, you can see the strong, so this is 25 and 20 kilometers. I'm showing here the model is the contour lines, and the colors are from a satellite climatology combining SAGE 2 and Clay's measurements from multiple wavelengths. So here you can see in the tropics larger values compared to the mid latitudes in the effective radius, which is captured well by the model, and then the decay in size through the period is in quite good agreement against these measurements. So this is very encouraging for the way the microphysics and the dynamics is representing the evolution of the. Yeah.
Why did you choose 15 to 20? Because Pinatubo is like at about 49.
49.
No, I guess not. I'm sorry. I'm thinking about Mount St. Helens. Never mind. Take that away.
Okay. So, no worries.
Sorry.
Yeah.
Sorry, Graham. Surface area density, is that from the latest data set derived for CCMI, or is that the old one that was, because you 2003, I think, right?
So I'm only showing the surface area in the top left plot here, and that's the model. So I'm not comparing here the surface area to measurements. It's only the effective radius that is in those right hand plots, and that's from the Baumann et al. Paper. Sure. So yeah, just to say really that I've drawn those vertical lines there to show. To represent the point of the eruption, and then the second vertical line is at the peak of the surface area density you see in that top left plot. And if you look then at how the size evolves, you can see that actually the size peaks in those latitudes much later than the peak in surface area. So you can see actually the size does not vary in proportion to the evolution of the surface area. In this case, the processes are continuing to shape the evolution of the aerosol after the peak of the surface area. And you see this also in the right hand plot, the increase in, I put those two lines on again, and you see really the evolution of the size distribution there is qualitatively well captured compared to the measurements. So we went further than looking at effective radius in terms of particle size, and compared to the balloon-borne measurements from Laramie in Wyoming by Terry Deschler, and here we're showing the vertical profiles from March 91, 92, 93, 94. So each coloured line there is showing a different subset of the aerosol increasing in size from the black at radius larger than 5 nanometers, then to red being really 150 nanometers and orange 250 nanometers. And those red and orange are really the main scattering area of the model. So the black are much too small to interact with the radiation. But once you get into the red and the orange, and then to the larger, coarser size channels, your scattering properties are changing rapidly. So it's very important to capture the variation of the size distribution across those channels. So this is what we're testing in the model. This is quite a stiff test for the model to see how it's doing. So if you see before the eruption in March 91, the model's capturing the variation really quite nicely against the measurements. So you capture the really smallest subset of particles down at up to 5, including all to 5 nanometers, and also the 150 nanometer concentrations. And then there's a big increase in those 150 and 250 sizes in March 92 from the big perturbation of the injection, but the black line is only slightly enhanced. So these are really all growing up to 150 and 250 nanometers, and you can see the model in the solid lines is capturing that really quite well. Even, and then as we look to the broader, the coarser size channels, we're capturing that profile in nice agreement with the measurements. So this is very encouraging. But and then as you can see some overestimation in the lowermost stratosphere there, and you can see that the N150 in the later years is a little too high against the measurement. So we do have a high bias in the smallest particles with a delayed recovery to the background. But this is very encouraging. So in the interest of time, I'll skip this one, but this is just some sensitivity simulations to test the sensitivity to uncertainties in some of the microphysical processes. But I want to move on and briefly talk about some work we've done since that paper, where we're actually now looking at the impact of the radiative coupling on the model, both in terms of the dynamics and in terms of the aerosol properties. So here I'm showing the tropical zonal mean zonal wind evolution in the vertical profile through 91 to 95. So you can see the signal of the semi-annual oscillation at the top of the domain, and the QBO, the quasi-biennial oscillation, really captured quite nicely in the model. So we initialized our model to make sure it was in the easterly phase with easterly zonal winds at the time of the eruption, as seen in the analysis. But here I'm showing now what happens when. So the top plot is without the injection of SO2, and the bottom plot is with a 20 teragram injection. And so that second vertical line is really drawing the cross between 30 hectopascals and the 10 meter per second zonal mean contour. So you can pick out in the in the lower stratosphere there, where that's being moved to. So what you see is that with the dynamical effects now in these radiatively coupled simulations from the aerosol heating that I mentioned, it's really blocking the downward propagation of these of the momentum, and it's locking the QBO easterly phase to several months later into around April or so. Now, if I show now the era interim reanalysis, you see this extended easterly QBO phase in 1992. It's actually stronger than in the model, but we're qualitatively capturing that response really quite well. So then if we look at the aerosol evolution, here I'm comparing a 20 teragram injection on the top with no feedback on the dynamics against a run with the feedback on, and against the measurements. And here you can see the 20 teragram is generally is much too high in the mid latitudes against the measurements, as we saw before. But you see the effect there in the reduced AOD in the tropics from this enhanced upwelling, bringing in sort of fresher air, and also much increased transport to the southern hemisphere. And so this is only one ensemble member, but you see already the effect there of resolving this coupling. And here I'm really showing now three ensemble members on the right hand side. So this is the difference between a Pinatubo and a no Pinatubo run in stratospheric optical depth. And you see some variation. These are three different initializations, each one being in the easterly QBO phase. But broadly, you see that same picture happening. We've got so this is for 14 teragram eruption, and you're getting this transport to the southern hemisphere enhanced in the simulations compared to the uncoupled runs and the reduction in the tropics. And now we're now looking at the impact of that change in aerosol on the aerosol forcing itself. So here I'm comparing the shortwave top of the atmosphere effective radiative forcing is in the coupled runs, which is shown in the dashed line. So if you look at the top left and the top right, first of all, your solid line is our diagnosed aerosol forcing, shortwave forcing at the top of the atmosphere from our uncoupled runs. The dashed line is from the coupled runs. So these are both 20 teragram runs. So the top left is near global, and the top right is in the tropics. And we're comparing there to the Irby anomaly from that was reanalyzed in this Wong paper in 2006. So this is, you can see that from this single ensemble member, what you see is a reduction in the peak forcing and a longer decay of the forcing signal, which is sort of what we're, particularly in the tropics, we see this reduction in the tropics, which is what we saw in the AOD, being lower, and the transport to the southern hemisphere and the north and the mid latitudes we saw was enhanced in those runs, and you can see a generally in better qualitative agreement with the decay timescales in the observations there. But this is clearly showing we are overestimating again with a 20 teragram injection. So this is consistent with also the direct aerosol measurements. And now, so in the bottom two plots, we are showing three ensemble members in the fully coupled simulations for 14 teragrams compared to the anomaly from the measurements. So you see that we're still a little high against the solid blue line from these three ensemble members. So this is again in the tropics on the right hand side and near global on the left hand side. We're really getting a much higher effective radiative forcing than the observations suggest for this 14 teragram run. But what's interesting is if you look at the anomaly in these measurements, actually on the decay of the anomaly, it's kind of goes to, it's around 2. It's not at 0 as you follow the decay of the anomaly from the eruption. It sort of seems to be up at around 1 or 2 before the eruption in the tropics, and about 1 or 2 above 0 after the decay away. So just for fun, we actually, it looked like we were capturing really the shape of this decay. In the dashed line, the blue dashed line there, we've just moved we've added taken away an additional 2 watts per square meter, and I guess this is just showing how well the model is capturing the decay of the radiative forcing qualitatively against these measurements. But it's interesting to see then when you do that it then is around 0 before the eruption at the end. So the model here is predicting generally you'd think of a 3 watts per square meter shortwave forcing or so from the model. Here we're getting a higher forcing, which is in quite good agreement with the measurements if you consider an offset. But this is kind of pointing towards, again, 14 teragrams perhaps being too much in the models, and a stronger efficiency of the radiative forcing than is commonly thought. So this is quite a surprise to us, but is what we're seeing. So I must be running over time nearly now, so I will wrap up to skip over what I was going to talk about, which is also part of a Spark initiative on stratospheric sulphur. Just to summarise that what we have now in configuration of this new UK Earth system model, and this is has the aerosol microphysics with a stratospheric sulphur chemistry to simulate aerosoling chemistry and dynamics in a coupled way to cover both stratospheric and tropospheric conditions. So we've evaluated the aerosol properties in background and perturbed conditions, and we're really seeing that 20 teragram, which is commonly the number you think of around a Pinatubo injection, is over predicting our model, both the burden and the AOD peak in the model, whereas a 10 teragram seems in good agreement. However, when you looked at the extinction, we saw actually the 20 teragram was in quite good agreement. So there's some anomalies to reconcile there. But what I've shown then is as we've radiatively coupled the simulations, we're starting now to understand and investigate the responses to the aerosol, and we're now looking at the response of the ozone as well to the dynamical changes induced by the eruption. And we've seen that qualitatively this 14 teragram Pinatubo forcing captures the evolution quite well, but still seems a little high. Although there's some uncertainty there about the Irby measurements seem to drift back up above 0 in the anomaly, which we're trying to understand. And it'd be good to talk to people here a bit more about that, as we're relative newcomers to this field. But these are quite new results that I wanted to share with you. And then really this new Spark initiative to understand the stratospheric sulphur and its role in climate is going to be going on in the next few years. And one component of that is a big ensemble, perturbed parameter ensemble around the Pinatubo eruption. So each model is going to run an ensemble, and this is a real effort to quantify the uncertainty around the Pinatubo forcing, varying parameters within the ranges that we know. So this is going to be an exciting time over the next few years. So I'll leave it at that.
Graham? Okay, do we have...
Hey, kind of pleased to see you found very much the same thing we find in Wacom in terms of the SO2 burden. And we had a number of issues reconciling the 20 teragrams of SO2 not getting the right responses in terms of AOD and temperature responses. And in fact, I looked at the Sage 4 data, the Sage 4 Lambda data set that's used for the CCMI runs for prescribed aerosol, and that mass actually comes out to about 9.7 teragrams. So there's actually a paper by Guo et al. In 2004 where they look at the amount of SO2 from various satellites initially, and initially you do see a range from about 12 to 19 teragrams, but by 10 days later it's down to 10 or less, and some of that can be attributed to conversion of SO2 to sulfate, but there seems to be a sharper drop in the initial 5 or 10 days that they talk in the paper about how it may have been absorbed onto larger ice or ash particles that came from the eruption, and those subsequently fell out. So that could be an explanation for the initial high amount of SO2, but that didn't persist in terms of long-term amount of sulfate in the stratosphere. I don't know if you looked at that quote.
I referred to that paper near the start. Yeah, so I think the range they have is let's just go back to the plot. So they had between 14 and 23. So this was the plot from that paper, which is just showing from the 19th of June the TOMS image. So yeah, their range from combining the TOMS and the TOVS measurements was between 14 and 23. But as you say, that has quite a sudden drop down to around 10 or so teragrams after a few days after that. And yeah, they speculate about potential influences. One thing is the potential interaction with the ice or the ash in the early post eruption period. Another alternative they suggest is actually that the retrieval from the satellite could have been affected by the presence of ash as well. So it could be one of the, it's an interesting. Mm-hmm. It would be. I think it's funny that uncertainty is there, but if you ask people what how much SO2 was injected, everyone would generally say 20 or 17. So it's suddenly there's been a big, I guess it's interesting that your group find it as well. And looking back at some of the other papers, you see a high bias that it seems inconsistent with those large sulfur injections.
You said in your conclusions that the extinction in the lower stratosphere for 20 looked better than for 10, where AOD is the sum of extinction. So is that just a altitude distribution issue? Or?
So what I was showing was that if you look at this plot in the mid-latitude, northern hemisphere mid-latitudes, you would say that the 20 teragram run in the top left was much too high against the measurements, whereas the 10 teragram seemed in good agreement in the northern hemisphere mid-latitudes. Whereas if you look at the extinction in the mid-latitudes, the red line there is the 20 teragram run, and the orange is the 10 teragram run. So if you look at the lowermost, and this is on a log scale, so it's a little hard to see. I can see it from here, but you probably can't see it. But actually, it looks from those comparisons that the red line is in really good agreement, and the orange is a little low. So particularly at the lower end. So I don't know. There is this issue about the retrieval at the lower altitudes. There's this known issue with the saturation, but it seems strange that the column AOD, as you say, which is then the integrated extinction in the whole column in the stratosphere, is something that we're still trying to understand. I know there's this new paper about the Nabro eruption and comparing to the Osiris extinction profiles, and seeing that at the lowermost stratosphere, some of that is missing some of the signal. But I've no idea if that could be an issue here. It's certainly there's uncertainty. And you mentioned the injection height, which obviously we know the injection height range has a big control over the evolution, and I already showed that the dynamical effects also change the evolution quite a bit. So I don't want to draw too much, but I think that is a broadly, it clearly sees that the 20 teragram is too high compared to the 10. But it's it's an interesting question.
Let's take one more question in the interest of time.
Nice talk. I have a question. So, do you think what's the lifetime of volcanic aerosol in stratosphere? Will the lifetime depend on how much SO2 you emitted to the stratosphere? I think this is a question associated with geoengineering as well. So if you put sulphur into stratosphere, how long the effect will vanish or disappear?
Yeah, so the lifetime. I mean, one thing actually is that the different sized particles have different lifetimes. So I haven't shown it here, but if you plot out the time series of the different size channels, say from that we've compared against the OPC, then the coarser ones, of course, are more influenced by sedimentation, so they're removed more rapidly, and the sort of 250 nanometer size channels, you can see, has a longer decay timescale as a result of the different influence. So, but the lifetime, I guess, then it's varying between those channels between maybe 1 or 2 years. So I think the finer, as I mentioned, the decay of the 150 size channel here, you can see, is slower. The e-folding time, I guess I'm talking about the e-folding time scale here. So we do characterize that in the paper, but you can see that in our model, the N150, this is one I didn't show, but the bottom two plots are showing the 150 size channel at Laramie compared to the measurements, and we get quite a longer decay in our model compared to the measurements. But this is it's an interesting question, and it illustrates the importance of capturing that variation in the size distribution to make sure the radiative effects in the shortwave and longwave are captured through that period.